All right, so first of all, I want to stress that there's not only one way to do these. So just because you didn't do it exactly like we're about to do it, it doesn't mean it's wrong as long as you get to the same answer at the end. All right, so number one, obviously they all say simplify the given expression. Number one has secant x minus 1 times secant x plus 1. So what would you start by doing? Foiling it out. That's going to result in the difference two squares, right? So I can use the shortcut, which is square the first one and then square the second one and then put a minus between them. And I get secant squared x minus 1. And then because there's a squared and there's a 1, I would have gone to my Pythagorean identities. So sine squared plus cosine squared equals 1. Tan squared plus 1 equals secant squared. And 1 plus cotangent squared equals cosecant squared. So by looking at those, I know I'm going to the second one. And if I had to move the 1 to the side with the secant, it's left with what? Good. I would get tan squared x. You could have like long way around. I could have made them 1 over cosine minus 1 and then 1 over cosine plus 1. I could have combined them into one fraction. Sure. And then I could have gone from there, but I think that that's probably the easiest way to do it. All right, 2 said secant squared x times 1 minus sine squared x, and I've got the 1 minus sine squared. So again, I would, because it's got the squared and it's got some sort of sum or difference, I'd go to my Pythagorean identities and see if there's one that's got 1 in sine, and there does. It's the first one. 1 minus sine squared will result in cosine squared. And then what is secant if I rewrite it? Good. This would be 1 over cosine squared x times cosine squared x, and then the cosines cancel, and I get just 1. Good so far. All right, then I get secant x over cosine minus tangent x over cotangent. So give me one method to do this, because I would say there's two that most people try. What's one thing you could do? Yeah.
Change flip on either side and do 1 over cosine x times 1 over cosine x?
Sure, so we change this to 1 over cosine x over cosine, and then you keep change flip 1 over cosine, and I get 1 over cosine squared x. And then on the right, you did the same thing? Did you make a sine over cosine, or did you leave it?
Tangent x over 1 times tangent x over 1.
Okay, so this becomes 1 over tangent x. So when I flip it, it becomes tangent. So I get 1 over cosine squared x minus tan squared x. Then what?
And then from there, I change tangent squared x to sine squared x over cosine squared x.
Okay. Now they have the same denominator, so 1 minus sine squared x over cosine squared x. And 1 minus sine squared is?
Cosine squared x.
Cosine squared x over cosine squared x, which is 1. Good. Questions on that method? Anybody try the shortcut I taught you last week? Anybody remember the shortcut? What happens if I move something from the top to the bottom or bottom to the top? It becomes the reciprocal, right? So if I move cosine from the bottom to the top, what's the reciprocal of cosine? Secant. So that would become secant x times secant x, or secant squared x, minus. If I move cotangent from the bottom to the top, it becomes tangent. And then I get tan x times tan x, or tan squared x. And then I would have gone to my reciprocal identities, my Pythagorean identities, sorry. And I get tan squared x plus 1 equals secant. So if I took the secant and I subtracted the tangent from it, on the left side is just 1. Both give you the same answer. Okay, obviously the one on the right is a lot less work, but if you didn't see it, if you didn't do the shortcut, that's fine. Just try to think about stuff like that. Like if I can move from the top to bottom or bottom to top, it becomes the reciprocal function. Questions? Okay, so the good and bad of 5.2 is it is basically like 5.1. So if you hated it, sorry, it's going to continue. If you're starting to get the grasp of it, then fantastic. Everything we need to know, again, is on the same slide. And this, I said it last week, but I'm going to say it again. This is not given to you on your test. You have to know these. So we need to make sure we know our reciprocal identities. I feel like those are the ones we're the most comfortable with. Our Pythagorean identities, sine squared plus cosine squared equals 1. Tan squared plus 1 equals secant squared. 1 plus cotangent squared equals cosecant squared. Your even odd identities, and you'll know to look for these if I have negatives on my angles, whether it's an x or a theta, whatever's there. If there's a negative there, then I would know to substitute it for what it equals. So if it said cosine of negative theta, I would know that that's the same thing as cosine of positive theta. If it said tangent of negative theta, I would rewrite that as negative tangent of theta. So you're looking for the negatives on the angles for even odd. And then the last one is your cofunction identities, and these scare people, but honestly, they're probably the easiest to spot. If there is something with pi over 2 minus an angle, or 90 minus an angle, because those would be equivalent, then I just need to know what to replace it with. So sine pi over 2 minus an angle equals cosine of that angle. Tangent goes with cotangent, secant goes with cosecant. All right, so here on this slide is some like strategies, okay? And I wouldn't say I probably do all of them, or there's not even a specific order, but these are like, how do I start this out? So the first one says work with each side of the equation independently of the other. So really, you can only, the goal is to change just one side. If you're going to modify both sides, you cannot cancel things out. That's the biggest thing there. You can look for opportunities to apply the fundamental identities, which are your reciprocal identities, all those things. Usually we're going to look at the more complicated side. There are going to be times in which you're going to have to factor out the greatest common factor. There's going to be times in which you multiply. And then that next thing says separate single term quotient into two terms. So if I have a fraction and it starts out as a sum or a minus, I can break these apart by rewriting the terms of the numerator over the same denominator. So if it said tan of theta plus cosine of theta over sine, I can separate them out, and it would be tan over sine and cosine over sine. So you would separate them out, and they both get the same denominator. The reverse of that is if you have to combine fractional expressions. So if I had something like what's here on the right, I would combine it to get to the left. Usually that means we have to find a least common denominator. So if you've got two fractions, you want to get it down to 1 by finding a least common denominator. And then sometimes we have to multiply the numerator and the denominator by the binomial factor that appears on the other side of the identity. So if you're setting it equal to something, sometimes we have to move from one side of the other by multiplying by what's on the other side. Okay. Here's the biggest thing is don't be afraid to stop and start over again. Sometimes you get to a dead end and you can't go any further, and it's okay. You got to stop and go back to the beginning and see if you could start it a different way. All right, so the good part about 5-2 is there is an equals there. I know when I am done. I need the left side to equal the right side. So if you look at this one, what's more complicated, left side or right side? Left side. So I'm going to work with the left side. What is there that we can substitute? Sine squared plus cosine squared is what? 1. And I get cotangent squared x plus 1. It doesn't equal the right side yet, but I get cotangent squared x plus 1. Where did we see that? Your Pythagorean identities, right? What's the Pythagorean identity with cotangent and 1? It says, in the order, it says is 1 plus cotangent squared equals cosecant squared, but order doesn't matter when it's addition. So this can get replaced with just cosecant squared x. So the goal, again, is to get the left side to equal the right. That last step has to have the complete statement. Left side equals right side. All right, example 2, tan squared minus sine squared equals tan squared times sine squared. So what's more complicated, a sum or a product? The sum. I got to get the left side down to 1, get rid of the subtraction sign. So how can I rewrite left side?
Like sine over cosine.
Okay, So, and first of all, I would say, because they're squares, I would have looked at my Pythagorean identities, but there's no Pythagorean identity that has sine and cosine, and tangent and sine together. So I would know I got to do it differently. So I can rewrite tangent as sine squared x over cosine squared x. Now, if I want these to be one term, I need to give sine the denominator of cosine. So I'm going to multiply by cosine squared of both the top and the bottom. And I get sine squared x minus sine squared x cosine squared x over cosine squared x. Now what? So from the right-hand side, I could cancel the cosines, but I can't from the left-hand side. Right? Like I can't do just this because it's got to come off of both.
You can divide sine squared x.
So I can take out a sine squared x. Now what? What is 1 minus cosine squared x? Sine squared x. Now keep checking it, like back with what I want to get to. Am I getting closer? Yes, I've got it down to just one term now.
How'd you go from negative sine squared x times cosine squared x to 1 minus cosine?
So for this one, we took out sine squared. It's the greatest common factor. So by taking it out, we're dividing this by it and this by it. So this becomes 1. Hello, and these cancel. Ari. Does that make sense?
But then you kept the sine squared x.
Because we just took it out.
Okay.
We're not actually getting rid of it. We just took it out, factored it out. All right, so now if I have a product in the numerator, right, and it's not a sum or difference, can I break this apart? Can I separate a fraction like that? Can I say that that is sine squared times sine squared over cosine squared? Yes, I can't do that with a sum or difference, but I can do it with a product. And what is sine squared over cosine squared? Tangent. So I could have done it that way or I could have gone the other way. It doesn't matter which one. One of these gets the denominator if it's a product in the numerator. If it was a sum or difference, they would both get the denominator. But as it is, they are both. So I can rewrite this as sine squared x over cosine squared x times sine squared x. And then sine squared over cosine squared is tan squared. And now the left side equals the right side. Questions on that one? All right, go to 3. What can we do here?
You could change it to cotan. No, you can't. See it.
Change flip both of the fractions.
So I can make this 1 over sine, is that what you're saying? And make this 1 over cosine. And then when we keep change flip, that's my shortcut, right? Bring this to the top. And it becomes, if you bring cosecant to the top, it becomes its reciprocal function. So we're multiplying times sine. Bring this to the top, and it becomes its reciprocal function, which we're doing the same thing. This becomes cosine. And now I get sine squared x plus cosine squared x. And that is 1. Can I go anywhere with 1? It's like a dead end, right? What happens now? Look at the right. What can I do on the right?
Divide the cosecant. Yeah, divide
What does cosecant become? 1 over sine x, and this equals 1. So there are times when you get to that dead end, right? You could have also, from here, I could have divided both sides by sine. And I get cosecant x equals cosecant x, so that works too. There's a couple different ways to do it. Or divide by cosecant, and 1 over cosecant becomes sine, as long as at the end the left side equals the right. Questions on that one? All right, example 4. What's more complicated, left or right?
Left.
Left. What do we do there?
You can do 1 plus tangent squared x. You could convert it to cosecant.
Good. So 1 plus tangent squared is in my Pythagorean identities. If I go look at my Pythagorean identities, it says tan squared. Plus 1 equals secant squared. Now what? If I know I have to get rid of the denominator, right, because I don't want a fraction on the right-hand side, what happens when I move tangent to the top?
Turns into cotangent.
It becomes cotangent. So now I get cotangent squared x times secant squared x. And cotangent is what? I would go to the right and look, okay, obviously I need to get it down to one term.
Sine over cosine.
So cotangent is cosine over sine. Cosine squared over sine squared. And what is secant squared? 1 over, almost, cosine squared, right? Now what?
You get 1 over sine squared.
Good, cosines cancel. I get 1 over sine squared, and 1 over sine squared is
Cosecant.
cosecant squared. All right, last one. So now there's fractions on both sides. But on the left, I get sines and cosines. Like, I'm not going to convert that to the reciprocal function. Sometimes we can. But instead, I'm going to try to go to the right-hand side. I can replace tangents with what? I could do 1 over cotangent. I can move that to the bottom. But if the left side is sine and cosines, I know I'm going to eventually have to get to those terms, right? So what is tan squared rewritten as? I mean, sorry, tan rewritten as? Sine over cosine. 1 plus sine over cosine. Now what do I do in that denominator? What does 1 become if I want to give it a like denominator? Cosine over cosine. So my numerator is sine x over cosine x, and my denominator is cosine x plus sine x over cosine x. Now I've got a complex fraction, right? So I'm going to flip it. This becomes cosine x over cosine x plus sine x. So this is gone. And the cosines cancel. And I get sine x over cosine x plus sine x, which is the same as sine x plus cosine x. So that time they both started with fractions. They both had multiple terms, but I know that I can tweak tangent, I can play with tangent a little bit easier than I can play with sine and cosine. If you're in your fundamental ones like sine and cosine, and then there's ones that have the reciprocal ones, you're going to definitely go with those. Any questions on the web assign that was due this morning? So if you don't have questions, you can open tonight's homework is a PDF. Okay, you need to show the work for these. You're walking them through step by step. Don't skip steps. If it's a variable you don't like if they have theta and you'd rather put x, that's fine. Just make sure you put it back at the end. And you can shorthand stuff, like you could write s squared plus c squared equals 1, like that kind of stuff. But make sure you justify your steps. If you are using the shortcut, so let's say it said sine x over cosecant x, and I'm bringing this to the numerator, you have to show it that way. You can show it that way. You can do keep, change, flip. But if you're moving it, you got to show that step. You can't skip steps on these verifying ones. The work is how you'll get the points for these. Yeah.
11 and 12 on the other side.
Sure. All right. So I will tell. Did you start it?
What do you mean?
Like, how did you start it? So what was different for everybody was that term on the front, the red one. God bless you. But if you take that out.
I mean, I literally got it right. It's just backwards. It's backwards.
Yep. So the numerator, like if I replace that with tangent squared, God bless you, which you can't get rid of the secant in the bottom. So because they are both secants and the top is the difference two squares, that's where you want to factor it. So it would have been 9, guys, plus 1, and then secant x minus 1 over secant x minus 1. And then the minus ones cancel, and that's the answer. So I would say if you have, if you see, and I could have even done the difference of two squares in the top, but then you have to take out the 3's, it gets messy. If you see something you could factor out from the beginning, do it.
Yeah, that's what I did, but I didn't know if the simple question was where I had to distribute.
No, I mean, and I would give you both. You see it marked both right. Like this had the 9 and this had the 9 on front. Both of those would be fine. All right, then 12 said factor the expression. So do you substitute in for A or do you keep them as cosines?
I thought I had to do some quick add and identity.
Oh, okay. Because they're both the same trig function, I would have made A equal cosine x, the middle one. So then it's 8a squared plus 18a minus 5. And then first times last here, factors of negative 40 that sum to 18 are negative 20, positive 2. No, positive 20, negative 2. Replace your middle term. And then factor by grouping. And then take out a negative 1. The parentheses are the same. And then at the end, you just got to put the sign back in. And that's as simplified as it gets.
Yeah, I didn't see the word factor.
Oh, that sucks. Yeah. But it may not, we're going to get to ones when you start to solve these. So the next section is solving these. And it wouldn't necessarily say factor. You'd get an equals in there. And so as soon as you see the same trig function, cosine squared, sine squared, whatever it is, if you see them both, one as to the first power and one is, that's your hint. You have to factor. Yeah. You're welcome. Any other questions on the web assign? So again, kind of like what we were just saying, as soon as you see the same trig function repeated, it's just like it would be x to the third, x to the second, x to the first. So this is the factoring by grouping because there's 4 terms.
Yeah.
So if you make cotangent your a, then this is 4a to the third plus 4a squared plus 4a plus 4. And then you could take the 4 out all the way, or you could factor by grouping here. Take out a 4a squared, a plus 1, take out a 4, a plus 1, and then 4a squared plus 4. And your a's are your cotangents. So you could have even taken it a step further and taken out this 4.
That's right. Yeah.
And that's right, actually. So it would have been cotan squared x plus 1. That's the most factored form.
Or no, that went to cosecant, right? Or the cotangent.
Oh. This actually gets replaced. That's what you're saying? Yep, that's cosecant.
And then I try to solve it with the 4 cosecant times cotangent plus 1. Like, because it was a regular cotangent.
Like if you distribute it in.
Oh no, I just went 4 cosecant. Yeah.
You distribute it in. Which I think is still fine. Yeah.
Because I got it wrong, but I don't know if I got the answer right. Because I got 4 and 1 over 1 minus cosine. It's just 1 over.
Oh, you just replace cotangent. So it's simpler to leave it in fraction without the fraction form.
Okay.
Yep.